Okay, here we're going to introduce our breast histopathology images, and we're going to classification the breast cancer subtypes. And here's our outline. There are mainly 5 outlines for it: introduction, related work, proposed method, experiments, and conclusion. We're going to say about our motivation. The breast cancer is one of the most prevalent disease among women in our country, and it's good to have a reliable method to make our breast cancer classification text better, because in the traditional breast cancer diagnostic methods it's not really accurate for it. And here's some limitations for the machine learning techniques. At first we got our SVM, and there's some limitations of in dealing with high dimension and nonlinear data. Then here's the random forest, and the best limitation is it's unable to automatically learn deep features from images. So that definitely won't be our method. And it's the clinical applications. For clinical applications, there have to be a model to handle large-scale breast cancer images data. And it's gonna be reliable, because in the medical field, it have to be better and better to make the diagnosis really accurate to develop treatment plans. And it's the limitation of BPNN. The training time is too long and it have a local minimum problem, so we're not going to use it. Then we have 3 goals for it. The first goal is we're going to build our model based on the CNN based this convolution networks, neural network, and to extract deep feature from the image data. Then to provide a stable, efficient training process, we use IDC to do the classification, because there's a lot of subtypes in breast cancer. Then furthermore, the most important part is the convolution mode block attention model, CBAM model. It's the main part in our method, because in CNN there's also the ability of extracting features from image. Even CNN is very good of extracting features from images, but CBAM can extract different features from the images, and we'll explain it later. Okay, here's some related work we just said, and here's the summary of it. For the traditional method, there's some limitations, and for the CNN deep learning method, there's also some limitations from extracting features from the images. And in the future, we're going to add our CBMA method to improve our feature extracting ability for the model. Okay, here's our proposed method. So we add one more layer in CNN model, and we use the IDC to classify cancerous and non-cancerous. Here's our data preprocessing. At first, we made our pixel easier to learn. We make it 50 to 50, 50 times 50, to make it suitable for the machine learning input. Then we normalize the data to ensure the mean is between 0 and 1. And the third part is because the data set. The data set is not balanced in the negative and positive data, so we limit it into 50,000 samples to make the data balance. There won't be unbalance in the 50,000 number. The fourth is we combine and shuffle all the data to ensure the distribution in each batch is good. Here's our model architecture. On the right hand side we can see our convolution layer. We have 3 convolution layers to make sure we extract enough features. But even that, we still got a extra 4th layer. It's the most important CBAM layer because we need to extract more features of it, and later we're going to say what's in it in the CBAM layer. And then we go into the flatten part. After the flatten part, we do the fully connected layers. Then we got our result: 0 for non-cancer, 1 for cancer. In the CBM layer, there's actually 2 layers in it. The first layer is CM layer. After the 3 layer of the convolution, we put the result into CM layer. CM layer will make the feature better to learn for the model. After that, we go to in the SM layer. SM layer is the most important part. S stands for spatial, to let the model know about some knowledge of spatial. It will have know the feature which part will be good for learning breast cancer classification problems. To solve the task by knowing which part of the images learning have the best feature to learn. Then we have our optimization part. So the loss function we use is binary cross entropy, and it's really fit for our task because it's a binary classification problem. And we use the atom optimization. We set the learning rate to 0.001. The third part is to prevent overfitting. We use mainly three methods. One is early stopping and drop out. The last one is we do the bench normalization. Here's the experiment part. The experiment part, here's some data preprocessing part, just like we said. So first we have 2 classification, the negative and the positive. Then we make the image to small fragmentation 50 to 50 and provide it into the RGB form. And here's our evaluation matrix. And in medical field, we think record is more important than precision because we don't want someone having some wrong judgment from the model. So recall is more important than precision. And here's some way we calculate the score for the model and the experiment detail. So first we have improved the feature extraction. The CBAM allows the model to focus on the most important part for the images and identify the key features. And then the 4 of it: enhance efficiency, increase robustness to data imbalances, and reduce overfitting. All of it is, we can do these 4 things is because of we identified the key features. We let the model to know about the spatiality of the images. So for like overfitting, we prevent it by using the better generalization for unseen data because we learn really good from the special features and increase the robustness. Also enhance the efficiency because the thing we learn is very valuable. So we can enhance the efficiencies by just learning a little bit features of it. And here's our ablation study. And the first thing we're going to mention is the traditional CNN and our method. We can see, wow, that's 21% improve in the F1 score. So it's basically totally better than the traditional methods because it can extract more feature and it can know about some spatial knowledge about the images. But that's not the only study we're going to say. The second study we're going to say it we compare it with the traditional attention. We also got a CNN plus attention layer version. But the thing we're going to say in it is the CBAN. They got the spatial knowledge of the model. So in the score we can see even the attention one improve it very much in F1 score. But we still can see with the spatial knowledge we can have a better score than just normal attention. Not only make the feature better, it's better. We only improve the other part for the model. So in the conclusion, this study integrates that the CBAM into CNN architecture can improve the model performance by dynamically focus on certain regions. And our special features about the spatial knowledges to make higher accuracy and better robustness. So here's our study. Thanks for listening. Okay, today we're going to introduce our CBAM attention layer plus CNN. And here's our demo video. And at first we're going to import some libraries. Here's the libraries we've used. Then doing some data readings, and we separate our data into negative and positive for non-cancer and cancer. Here are some visualized results about the data we use. These are all the cancer images. Then we going to do some data preprocessing of the images. So we set the images into 50 times 50 and 3 channel of the RGB. And for balancing the images, we set a limit about 50,000. So 50,000 for non-cancer and cancer to balance the number of it. Then we're going to put it into 2 arrays. Here's some details numbers about the photos we have done for data preprocessing and some visualized image. Then we separate our training data and testing data about 7,000 and 30,000. And here's the data we're going to show in the training and testing. It's 50 times 50 pixel. And we're going to build our CNN architecture. So we're going to have 3 layers. The first convolution layer, second convolution layer, and the third convolution layer with CBAM attention. Then we're going to flatten our layers and create our model. To create our model, and here's some summary of the model. Here's our some parameters and our output here, and which these are the layer names for what we're going to do. Okay, and here's some our details. And the total parameters we use is about 200,000. And then we're going to train our models. And after training our models, here's our the model accuracy, and here's the model loss. As we could see, as more EPA as it goes, the higher accuracy it it comes, and the loss goes down. So we can prove that the model is useful. Okay, and then here are some scores we're going to calculate, like accuracy, F1 scores, and here's the result. And we got our visualized confusion matrix, so we can see the model did pretty well. And here are some performance of the model. We can see there's 4 bars in the chart, four bars in the graph. First is the accuracy, F1 score, recall, and precision. After these four, we can see that the numbers are pretty good. It's all better than 90% precise. And in the end, we're going to test our model. So here's the test image. We also pre-process it into 50 times 50, and it is a cancer image. So we can see we printed out the prediction and the label. It's the same thing. So we can prove that the model is working well. Okay, here's our demo video. Thanks a lot.